My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will discuss page tables. Page tables are data structures that store mappings between logical pages in process memory and physical frames in RAM. These structures are used and managed in different ways on different systems, often with assistance from the hardware. At the end of this lecture, I will discuss extended page tables, which are useful for allowing hardware to support multiple simultaneous operating systems at once. Recall from the previous lecture that the page table stores mappings between page numbers and frame numbers. Whenever a TLB miss occurs, the page table must be searched to find the appropriate mapping. CPUs have differing levels of support for managing and searching the page tables automatically. On most modern systems, including x86-64 and ARM CPUs, the page tables are managed and searched by the CPU automatically upon a TLB miss. This search increases the memory access time, but no fault or interrupt is generated. As a result, the CPU does not have to perform a context switch. Among a few other CPUs, the MIPS architecture requires the operating system to manage and search the page table. Whenever a TLB miss occurs, the CPU triggers a fault, which is a type of interrupt. The CPU must make a context switch away from whatever task is currently being executed in order to execute the interrupt handler for the fault. Software-managed page tables are becoming increasingly uncommon even on embedded systems, as the popular ARM CPU supports hardware management. The MIPS CPU is typically used in lower-end consumer devices, such as inexpensive e-readers and the least expensive tablets. One approach to reducing the page table search time whenever a TLB miss occurs is to store the page table as a tree instead of a list. This technique of hierarchical page tables divides the page tables into pages. Each logical address in process memory is divided into an outer page table, a set of offsets into various levels of subtables, and a final offset to the specific byte of memory to be accessed. This technique can be generalized to any number of levels in the hierarchy, but I will present here a simple system that uses only 2 levels. As illustrated in this diagram, the data structure is arranged so that an outer page table provides a mapping between outer page numbers and page table pages. Once the proper page table page is located, the translation from page number to frame number can be completed quickly, since the page of the inner page table is relatively small. The address translation mechanism used with hierarchical page tables is more complex than that used with a simple linear page table. The logical address is divided into additional components. In this example, with 2 levels in the page table, the logical address is divided into an outer page table entry number, T, which specifies the location in the outer page table in which to find the proper inner page table. The next component of the address, P, is the offset into the inner page table at which the mapping can be found. In this example, we have a single page-to-frame mapping in each inner page table entry, so we can obtain the frame number from that entry. A real system will be more complex and likely will require a short linear search at some level in the page table. Once the frame number is determined, RAM is accessed in exactly the same way as it is in simpler designs, with the final address joining a frame number and offset into the physical address. Storing the page table in a tree improves access performance. However, as the total amount of system RAM continues to increase with newer and newer generations of computers, the size of the page table also increases. Moreover, the address spaces on 64-bit architectures are much larger than the amount of memory that the MMU actually supports. Current 64-bit systems have true hardware address sizes in the range of 34 to 48 bits. If we were to store a mapping to handle every logical page number in such a system, the mapping would be large and inefficient, since the address space is sparse. That is, not every 64-bit logical address can map to a physical location in RAM, since the physical addresses are at most 48 bits. As a result, many of the possible 64-bit addresses are unused. A solution to this problem, which both reduces page table storage size and increases search speed, is to use a hash table, or dictionary structure, to store the outer page table. Since several addresses may hash to the same value, each entry in the hash table is an inner linear page table, which allows the hash collisions to be resolved through chaining. Translating a logical address to a physical address with a hashed page table begins by hashing the page number p. Hashing is accomplished using a hash function, which may be implemented in hardware for high performance. The hash value returned by the function gives the location in the hash table where the inner page table may be found. A linear search of the inner page table is performed to locate the frame number. Once the frame number, f, is obtained, it is joined with the offset, d, to give the hardware address. Some architectures, notably PowerPC and Intel Itanium, store their page tables backwards. That is, the system stores a data structure with one entry per frame, and the entry stores the corresponding page number along with the process ID of the process owning the page. This approach, called an inverted page table, is efficient in terms of page table storage size. However, inverted page tables are inefficient in terms of performance, and these structures are not used on a majority of systems. On newer x86-64 systems with virtualization extensions, hardware support exists for extended page tables, or EPT. AMD and Intel each brand this technique with a different name. AMD uses the term Rapid Virtualization Indexing, or RVI, on newer CPUs. They used to call this technique Nested Page Tables, or NPT. Intel uses the Extended Page Tables terminology. EPT adds a level of paging to the system. At the outer level, each virtual machine, or guest, running on the CPU sees its own set of memory frames, isolated from and independent of the actual hardware. The CPU translates page numbers to frame numbers first by translating the page number to a guest frame number. The guest frame number is then translated to a host frame number, which is the physical frame number. EPT technology is important for virtual machine performance since it allows each guest to manage its own memory efficiently. Moreover, guests can access memory without having to switch the CPU into hypervisor mode, which can be an expensive operation. The downside to logical address translation with extended page tables is that it becomes conceptually more difficult to understand, as illustrated by the complexity of this diagram. A process running in a guest operating system makes a memory request just as it would if no virtualization were present. This memory request is divided into a page number and an offset as usual. The CPU then performs translation of this page number, p, to a frame number, f, also as usual. Furthermore, as far as the guest operating system is concerned, the translation is complete. The guest OS sees the memory region provided by the host system as if that memory were physical memory. In other words, the guest OS has no idea that it is running in a virtual machine. To the guest OS, the virtual machine looks just like a physical system. However, in reality, the guest's physical memory is actually an illusion provided by the host. To make this illusion work, the host must translate the frame number, f, in guest memory to an actual physical frame number, g. This translation is performed by the CPU without any context or mode switches using the EPT table. Once this translation is performed, the physical memory address is generated by combining G and D, where D is the original, unchanged offset into the page. It is important to note that this entire process is performed by the CPU, without switching to the host OS or hypervisor.